because our lecture today is really short. So let's kind of take a look at what we were supposed to do. So, well, I'm not going to do exercise 1. That one's easy. You could just copy it out of the textbook. On exercise 2 on Blackboard, find a .wave file containing a text message encoded using Morse code. Write a Python script to read it in and plot its spectrogram. Add annotations to your spectrogram plot to indicate the location of the fundamental frequency. Blah, 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 all that fun stuff. Okay. So, import think DSP, import matplotlib.pyplot as PLT. And now let's do this. Let's say wave is equal to think DSP.readWave. Oh, I'm gonna need the waveform file. Hold on. Don't do it. Stop. Download. All right, there we go. Morse code dot wave, and then wave hold on, one thing at a time. Wave dot make spectrogram, and then spect dot hold on, spectrogram. Let's use expressive code dot plot plt dot show. Well, let's take a look at what that looks like. It looks like an error. Oh, might be seg length equals, let's go with 512. And there we go, right? So we popped up this dude right here. Hold on, let me see what people are typing. Can you show it? Well, yeah, so we're doing that right now. To get the FF, I use the spectrum graph to find it. Is that a valid method? Oh, I see what you guys are talking about. Okay, so a couple things to unpack here. Can I? Yeah. Wish I could draw on this. Okay, so here's what the spectrogram looks like. A couple of things that I realized in hindsight may have been kind of tricky, right? There's obvious frequency components happening here, right? So there's clearly this line here at 1,000. There's clearly a line at 3,000, clearly a line at 5,000. You can see at 4,000 and at 2,000, you can see signal components happening here as well. You might be tempted to come down here at around the 0 mark to go hunting for signals. Yes. To answer your question, Akil, yes, it's approximately just noise, right? So this would be the DC bias inherent in the signal, right? So everything that's sort of sitting around 0 is going to be just garbage. And so you don't need to worry about that. Can I like pan out? Or do I need to? Oh, there we go. Yeah. So you're gonna have a lot of stuff, and you got to be a little bit sort of think. You got to think critical just a little bit about the signal, because remember we talked about when you're thinking about whether or not this stuff down around 0. When you're thinking about the stuff down around 0 and whether or not that's real signal, go back to like when you play the signal, right? So if I play it, right, just like that, don't forget we talked a couple days ago about the fact that you will hear the dominant frequency, right? So if you listen to that, right, if you listen to that signal, it's clearly a high frequency signal. And you can sort of reason out that it's probably not, what you're hearing is not, you know, a 20 hertz or 40 hertz tone, right? That'd be a really low rumbling tone, right? That's not present in the signal. That's just going to be noise that was sort of built into that. That's just noise. is the punchline there. So from there, you kind of just go and look and say, what you should have done is looked here and said, all right, I got some frequency components. The lowest frequency component here that stands out is the one that's 1,000 hertz. So that's my fundamental frequency. And then you can just kind of zoom in on, you know, your stuff here. And you can see that you can hopefully look at it and see the Morse code, right? So there's dash, dash, dot, dash, space, dot, dot, dash, space, dot, dot, space, dash, right? And then just kind of decode the, you know, Google Morse code table and then type it up. So that was kind of that's what I was hoping for. All I was looking for this project was that you would do this bit right here. Just read it in, make a spectrogram, excuse me, run it, get this image, and say, oh yeah, fundamental frequency at 1,000, and then identify the dots and dashes that were recurring in the signal. Yes, the fundamental was 1,000. I mean, so Bashir asks, so are we looking only at everything at the 1,000 mark? I mean, you don't have to. I mean, remember, by definition, fundamental frequency is the lowest frequency component, which is we ignore the 0 stuff. We assume that's noise. And so the next one up is 1,000. So you should have, yeah. Because of noise, man. Because of that. So Keel asks, so Keel's showing this graph here, and he says, you know, so look at the spectrum of the first second. Can we explain why the amplitude was so high at 0? Red noise. Is the answer to that question. Remember, if we took the spectrum of our red noise or maybe our pink noise, it has all that low frequency component stuff in it. And then you can see, you know, 1,000. This is a great image. Hold on. Let me show everyone watching on YouTube what we're looking at. So Akil gave us this image. I think it was Akil. Yeah. So yeah, so if you just looked at the spectrum of the signal, then you would see, yeah, this big bit here at 0, right? You're always going to see that in any signal that you look at, right? That's going to be the noise, right? This is very similar to the pink noise spectrum that we saw last class. So you basically just ignore that. Anytime you see this sort of sliding up around 0, because you're not really going to be looking at signals with frequencies less than 100 hertz, right? Anything less than 100 hertz is going to be pink noise. So now you're kind of looking at the harmonics, right? So we have a clear peak here. That's definitely the fundamental frequency. And then you kind of watch them drop off here. Now, can anybody tell me what you think, like what's going on here? What's 2,000 and these other guys, right? 4,000, and then the stuff falling off here. Bet Edward's about to tell us. Maybe he's not. I don't know. Well, they're harmonics, but why is there a harmonic at like below 2,000 and above 2,000? Like these kind of split 1,000 and 2,000. Good. Curtis, got it. Curtis gets the gold star for the day. Yes, this is the aliasing. Remember that our folding frequency happens since we were doing this at what, like 11 kilohertz, I think. I don't remember exactly what the default frame rate is here, but yeah, the rest of this stuff is going to be aliasing that shows up. So we have fundamental, next harmonic, second harmonic, third harmonic, and then, you know, aliasing that happens everywhere else. So in fact, you could actually look at this and probably calculate what the fundamental frequency was from your signal. But yeah. So yeah, man. So Keel, did that answer your question? Cool. All right. Sorry, guys. Every like November, I get this like allergy cough from the like cotton being harvested. But of course, this year I start coughing and immediately I start having a panic attack. Like, this is it. We're gone. Okay. Any other questions about the assignment? Before we talk about what we wanted to talk about today. Hopefully a lot of partial. I mean, yeah, as long as you generated the plot, that was kind of the important thing. And then, you know what's weird before we walk away from this? Kayla, how the hell is your Python file 35 meg? It's all that malware that you're adding to your code. That bloatware, yeah. Because I mean, seriously, like, hold on, what was mine? Mine is 1K, which means it's probably less than 1K. How did you cram 35? And that's with also within. Well, I mean, I'm including ThinkDSP, but that's not really a thing. Crazy, man. Edward asks, was this Morse code signal generated from perfect sine / cos waves? I have no idea. I didn't generate it. I found a website that would just generate wave files of Morse code and use theirs. Oh, yeah, Akio, that actually probably is exactly what's going on. Yeah, don't open the .exe file in his submission. Truth. Also, one last thing before I walk away from this. If you looked at the low frequency components, they actually sort of weirdly appear in the gaps between the signals, right? So if you look at 1,000, it's like dash, dash, dot, dash. It's actually in the spaces between the signals is where this zero frequency component stuff happens. It's kind of strange. I wonder what causes that. Or is that maybe no signal? Is it the opposite of signal? Should have printed a legend. There should have at least been noise there. Curtis makes a good point. Maybe it just analyzes the background noise. Like maybe it normalizes, and then because that's what there was nothing else happening in that segment, and so it says, oh, there's clearly a lot of noise here, so there must be a lot of something. That's actually a pretty good hypothesis that we could test if we had time. All right, let us have class now. Okie doke. All right. So today we are going to talk about autocorrelation, which is a topic that we sort of briefly touched on in our previous life. But we're going to dig into it today and talk about there's actually some pretty cool stuff that autocorrelation does and leads to it. It's a pretty useful thing to be able to do. So, a quick overview. We're going to talk about what correlation means. We're going to talk about serial correlation, and then we'll talk about autocorrelation, and then we'll talk about autocorrelation of periodic signals, which is going to be our punchline here. So, let's talk about correlation. In general, correlation between variables means that if you know the value of one, you have some information about the other, right? So if we know some data, that can tell us some information about the other data. The most common form of correlation is this. It's called a Pearson product moment correlation coefficient. And it's basically just the, sum of the standard deviations, or it's the average of the standard deviations tied together. But that's not really important. You just need to know what it is and know that it's going to fall. The value of that Pearson's correlation coefficient is always going to be between -1 and +1. When the value is positive, that means that when one variable is high, the other variable is also high, right? When one goes up, the other goes up. When one goes down, the other goes down. And negative means that when one variable is low, the other variable is also low, right? When I think I screwed that one up. I did. That's a typo. When one variable is high, the other is low. So there we go. My bad. Okay. So positive is one variable is high. When they're positively correlated, then they move together. When they're negatively correlated, they move against each other. So, and that's going to be on a range somewhere between -1 and +1. 0 being there's absolutely no correlation at all between them, right? They're completely independent of each other. So let's take a look at calculating some correlation in Python. So here what we've got is first, let me make sure my little pin is working. Here's a function just to make some sine waves, right? We're going to create sine waves that two of them down here, but both at 440 hertz, and then we're going to give it some offset, right? And then we're going to make a wave. They're both going to be ½ a second long, and we're going to use a 10,000 hertz frame rate and return the wave. So we're going to create two of them. So they're the same signal. They're both sine waves at 440 hertz, but one is going to be offset by just 1, and that's 1 radian offset. And we'll go ahead and calculate the correlation coefficient using NumPy. So np.corrcoef of wave 1, just the values, and wave 2, just the values, and 0 degrees of freedom, but we're not going to worry about what that is right now. So when we plot it, we're going to get this. Again, this is kind of what we expected. It's two sine waves with a little bit of shifting between the two. And so when we calculate them, we get the numbers we care about are these guys right up here. And in Think DSP, he simplifies it just to give the correlation coefficient that you care about, which in this case, if we say wave 1 dot correlated with wave 2, gets us a value of 0.54, which is positive. And that makes pretty intuitive sense. They change at pretty much exactly the same time. There's a little bit of offset, but you know, when one is going down, so is the other, and when one is going up, so is the other, right? So that we can see that they're sort of correlated. And that happens vertically, by the way. So we're comparing like this point and coming straight down to like this point, and then moving to the next one, and then coming straight down to the next one, and we're kind of concerned with just that downward motion, right? So we're looking at a vertical slice still and seeing how that changes with change in time. So we do this and we see that these guys are both positively correlated with a correlation of 0.54, which is sort of decently strong, but not like super strong. It's not 0.9 or anything like that. And that's the gist, right? This is all we need to know for doing basic correlation, right? Wave 1 dot core of wave 2. If it's positive, it means they're moving together. If it's negative, they're moving against each other. -1 to +1. Any questions about just basic correlation? Cool beans. All right, so let's take that a step further, and let's talk about serial correlation. Serial correlation is correlation with itself. So, or more definitively here, correlation is defined as the correlation between each element and the next or previous element. So we're going to talk about the correlation between one signal kind of with itself, right? So our definition for calculating serial correlation here is pretty simple, but we're going to define a lag. So we're going to give a wave, or give it a wave as a parameter. We're going to define some lag value. So this basically lag equals 1 is the same as this, right? It's the same as shifting the wave over by 1 and then calculating its correlation. It's exactly what we're doing here. But we calculate two different values. So y1 is just, ys the lag point, and y2 is, shifted by lag. And then we calculate the correlation again using that NP or NumPy.corrcoef y12 and then degrees of freedom. So, and then we return the correlation. And here we're only interested in those this is how we get those, like just the value and not the entire matrix. So we index that array. Okay. Any questions about the definition here, right? So remember, lag is the integer number of places to shift the wave, and then we're going to correlate the wave with a shifted version of itself, and then we're going to sort of set what that lag period is going to be. So let's take a look at what serial correlation looks like with a bunch of different signals. So first off, let's take a look at signal correlation with white noise. So here we've created uncorrelated Gaussian noise, created a signal. Duration is half a second. Frame rate's 11 kilohertz. And we calculated the serial correlation of that wave. Now, white noise is completely random, right? It sort of completely is sort of randomly generated there, which means that we get a correlation of 0.006, which is basically 0, which is what we would expect, right? Since in fact, it's in the name, uncorrelated Gaussian noise, we would expect basically no correlation inside that signal, which is why we get basically zero or 0.006. I'm going to bet, I haven't tested this, but I'm going to bet that the 0.006 instead of just straight up 0 is because it's Gaussian noise, which is slightly, well, I guess you could probably argue that it's sort of correlated in that it's condensed, it's crunched down around 0, which is probably why we get a little bit of positive correlation, but really basically not. 0.006 is no correlation at all. But if we take that and compare it with Brownian noise, red noise, well, we're going to get a lot of correlation, right? Because it's this tight, I mean, there's noise that happens, right? But since it is correlated, red noise is our example of noise that's correlated, right? There's going to be a tight relationship between, you know, one point and another point in the signal. So we get a correlation that's basically 1, right? 0.999. So Brownian noise, red noise, is very tightly correlated with itself. It has a high serial correlation coefficient as compared to white noise, which basically has a 0 correlation, serial correlation coefficient. Let's take a look at pink noise. Now, pink noise is kind of strange because, remember, pink noise is kind of dependent on this value of beta. Remember that beta is going to be on a range from 0 to 2, right? And 2, when it hits 2, is basically red noise. In fact, it is red noise, or Gaussian noise. And so we're going to sort of slide from there. So instead of calculating serial correlation on just one signal, we're going to look at it over the entire range of beta, and that's what's happening here in this graph. Is we're starting on the horizontal axis, we're plotting beta, and on the vertical axis, we're plotting serial correlation. And we can see if we start with beta equals 0, right, we essentially have no correlation. It's white noise there at 0, and then it trickles up until it gets to really about the sort of 1.5 mark, where it's, you know, basically just red noise. So this is kind of interesting. This basically lets us sort of choose a range, right? This really illustrates that by setting the parameter beta, we can choose what we want, right? By setting beta equal to 0, we're basically going to get white noise. Going all the way up to beta is at like 1.5 is basically going to get this red noise, and so we can kind of choose what range on this spectrum you kind of want, and there's really a lot of reasons why you might want to choose one or the other depending on your application. So that's serial correlation, right? Taking the correlation of the signals with itself, and it tells us a lot about noise especially, right? So we can really identify noise based on you know, what its correlation is. So I think an example of a good test question here might be, you know, you imported a sort of unknown noise signal and calculated its serial correlation and found that its serial correlation was 0.65. What type of noise is this? Is it white noise? Is it red noise? Or is it pink noise? Good. Thanks, Curtis. Yeah, that'd be pink noise, right? So if you autocorrelation down around 0 is going to be white noise. Autocorrelation up around 1, or excuse me, serial correlation down around 0 is going to be white noise, and serial correlation up around 1 is going to be red noise. Anything in between is probably going to be pink noise. And I would write I wouldn't say like, you know, serial correlation of 0.1 and make it vague, right? So, but that's the kind of questions that you can expect to see for this one. And like I said, the big take home here is serial correlation is a great way to characterize your noise. Which brings us to autocorrelation. Autocorrelation is the next part of the chain, right? So you can think of, you know, there's correlation. And then if you do a bunch of correlations, you get serial correlation. And if you do a bunch of serial correlations, you get autocorrelation. Right? So autocorrelation is a sequence of serial correlations where lag is a parameter. Right? Here's how it's defined in the Think DSP library. You basically just create an array of lags, you know, starting from 0 and sort of working your way out. And then you just calculate correlation for each lag, and you're going to get correlation as a function of lag as you move forward. And then you usually plot, you know, lag down here on the horizontal axis and correlation there on the vertical axis. And here we can kind of also make a similar sort of determination. Notice that we've got different beta values plotted here. 1.7, remember that's basically white noise. 0. Wait, I got that backwards. My bad. No, erase. 1.7 is red noise. Beta equals 0 is basically going to be white noise. And 1.0 is going to be pink noise. And you can see how that affects the autocorrelation, right? So this red noise has this pretty stable downward sloping line. The pink noise has sort of a soft curve down to 0, whereas the white noise basically drops off immediately as soon as you stray too far away. And that kind of makes sense, right? Because it's noise. Remember, the lag is how far away you're moving from itself. How far are you shifting the signal over? So it makes an intuitive sense that even for a highly correlated noise signal like red noise, as you got farther away from the signal, you know, it's going to keep bringing, I mean, that correlation is just going to fall naturally as you move away from your original signal. Just the question is how fast. And in this case, you know, red falls off pretty slowly, pink falls off kind of at a moderate rate here, and then white noise basically falls off immediately. The moment you step away from your white noise there, your original signal, you're basically at 0. There's basically no correlation right from the beginning. So, any questions about that, about the autocorrelation signal? So it's basically, it's a serial correlation. You do it again. It gives you an alternate way to visualize your signal. Now, serial correlation and autocorrelation are pretty cool, but all we've been able to do with them so far is characterize noise, right? And we've spent like the last 2 lectures characterizing noise, which, you know, has its pros and its cons, but that's not what we get paid to do, right? We want to actually characterize some signals and make some observations and be able to process some signals. Well, this brings us to autocorrelation of periodic signals. So here's our scenario here. Suppose that we want to estimate pitch at any given moment of time. Now, remember, what is pitch? When we say pitch here, we're kind of referring to what we hear, right? And remember that we hear the dominant, which is often the fundamental frequency. So an alternate way to ask this question is, how could we estimate the fundamental frequency at any given moment in time? How could we see what that looks like? And so we have a signal here, or we have a spectrogram, right? And we can see that there's some signal down here around the sort of 500 hertz range, and it kind of falls off. And then you can also actually notice some like weird harmonics. And it's not showing up very good in PowerPoint, but if you go back and look at the picture, you can actually see these harmonics sort of rippling out away from the signal. It looks pretty cool. But we've got a pretty definitive signal here. But how could we do this with autocorrelation? How could we say, like, well, what is this signal? So the easiest way to do it, the way that would sort of jump into your brain is, well, let's just take a look at the spectrum. The spectrum will tell us what the signal is. And it kind of will do that, except, you know, we look here and we say, all right, well, we've got, you know, if I just sort of look at the peak here, the peak is, what, approximately 450 hertz. We know the author of the book likes music, so it's probably actually 440 hertz. But there's some problems. This doesn't tell us a whole bunch because the length of the segments, in this case, are 441 samples at 444.1 kilohertz, which means that the resolution is only about 100 hertz, which means that we've got like plus or minus 50 hertz on either side. So what's the deal there, right? There's a lot of range, and especially if you're characterizing like carrier signals or even just listening to music, right? A plus or minus 50 hertz swing is going to be a lot. So we need a way to sort of bring that resolution down. So what we do is let's go ahead and take a look at the signals. Let's think about the serial frequency or the serial correlation of these two signals. So he gives us this definition for plot, which is, you know, going to plot two waves sort of shift, or the waves sort of shifted a little bit, right? So we take one segment and plot it, and then we take a second segment and we're going to shift it off by some offset just a little bit and plot it again. And then it's kind of hard to pick up in the signal, but you can kind of see, if you look closely at it, you can see the offset signal just kind of hanging out on the edges here. And it's difficult to tell from this exactly what the frequency is, although you can kind of see that there's this wave, this lower frequency wave that's kind of present in the signal. And so the question is, well, how can we figure out what this wave is, right? Because we've got a pretty good idea that this is going to be our fundamental frequency, and that's going to be where we're at. And it turns out that by simply plotting the autocorrelation of the signal, if you plot the autocorrelation of a periodic signal, you will get effectively that big sine wave. So we plot the autocorrelation of our segment and plot it out, and then we can calculate the signal basically directly, right? So if period is equal to the lag divided by the frame rate, and frequency is 1 over the period, we can actually say that the main peak here happens at lag equal 101, which is going to give us a frequency calculation of 437 hertz. But what's cool is we brought that resolution down to plus or minus 5 hertz. So the take-home message there is, if you're digging around in a signal and you want to find the fundamental frequency of the signal, right? This even kind of relates back to the last exercise, right? If you've got a periodic signal and you want to say, well, what is the fundamental frequency? If you just take the autocorrelation and plot it, correlation on the vertical axis, lag on the horizontal axis, and look at your sort of fundamental peak there, and where is that in on your horizontal axis, you can calculate what that frequency is to a pretty high degree of accuracy. So, for example, in your capstone project, right, you need to sort of figure out what the sort of fundamental frequency of your tone is, and maybe a spectrogram isn't working because, spectrograms can be kind of confusing sometimes. Autocorrelation is an alternative for you to really dial in what your frequency is. So, any questions about autocorrelation of periodic signals? All right. It just occurred to me that I haven't put this on Blackboard yet, but I will put it up this afternoon, and I will make it due like on Monday, I think. But here's the exercise. We're gonna make some money. We're gonna do some day trading here. So here's what it says. At the website coindesk.com, you can download the daily price of Bitcoin as a .csv file over time. What I want you to do is read that file into a Python script and then plot the spectrum of the Bitcoin price. And then answer this question. Does the spectrum resemble white, red, or pink noise? What does it look like? And then using the spectrum of the Bitcoin price data, compute the autocorrelation of the Bitcoin price and say, is there evidence of periodic behavior in the price of Bitcoin? Could you use autocorrelation to predict when the sort of peaks and valleys of the Bitcoin price would be? So I think that'd be pretty fun. Any questions about that exercise? Okay, right. In that case, that's, like I said, I'll put that up on Blackboard here in just a little bit. It'll be due probably on Monday, I think. Yeah, make it due on Monday. And, well, that'll be that, man. All right, so just to recap, we actually used up most of the time. But we talked about correlation, talked about how to use correlation to calculate serial correlation, which is correlation on its own, on itself. And then autocorrelation, which is a series of serial correlations. It's like serial correlation. And then we talked about how we can use autocorrelation to identify the fundamental frequency of a noisy periodic signal. So, and that is it, man. Is there any update on the exam grades? No, there is no update on the exam grades. We will try to get them done by the end of this week. Our TA is proposing her dissertation this week, so she's a little bit busy.